Okay. Good morning, everyone. Thank you very much for your time. Sorry for keeping you waiting, but the Wi-Fi was giving us some problems. But we are on now, stable. Okay, so today is power generation and supply, and we will be going through some questions. So the questions have been sent to the class group, and it's in the description below, so you can download the questions from there. We just took all the questions in the slides in the unit 4 and 5 and put them together into one document. Okay. Into one document. So you have access to them. So we can start. Questions. So let's start reading the questions. So we must know first, please make sure you're familiar with the equations. Okay. Yes, let's be familiar with the equations. So when you get the question, write the parameters down. As we are writing the parameters down, you will know the equation to use. So a generation station has a maximum demand. So you've been given the max demand to be 35500 and has a connected load. So this is a demand, this is a maximum demand. Okay. So you are generating here. Then the connected load to that generator, the connected load is 65,000 megawatts. So the number of units generated annually, so units generated annually is given by 25.6 by 10 to the 7. Okay. Yeah, I think it's in watts per hour. Sorry. Watt hour. So the first question is for us to calculate the load factor. So as I said, you must be familiar with the formulas very well, because we know that our annual load factor is given by the number of units generated. Is given by the number of units generated over 8760 by the maximum demand. Okay. So this is the load factor. Number of units generated, we have it here. 8760 is a constant. The maximum demand, we have it here. So we'll just put it in it. And then we'll find our load factor. That'll give us 0.822. So please don't forget these formulas. Okay. Annual load factor is annual units produced over maximum demand times 8760. If it was monthly, this is the 87. This is what shows that it's annual. So they could have said find monthly load factor. I mean that this time it would have been the total number of hours in a month. That's 24 hours times 30 days. Yes, so you should know how to go about it. The next one is to find the demand factor. The demand factor is equal to the maximum demand over the connected load. Max demand over connected load, as we can see here. Okay. So we have the maximum demand, we have the connected load, put them together. So as the first thing is to write the parameters. If you write the parameters and then you start solving, you will know this one, the solution is here. So it's making it look easy in our eyes, but then maybe in the example it might not come to you easily like that. But once you write the parameters down, you just know how to go about it. All right. So that's this question. The next question is here. Okay. So the next question is, a generation station has given us a load. It has this load. So it has 15,000, 12,000, 8,000, 6,450 kilowatts. And it has a maximum demand of 2200. This is a maximum demand. Okay. So now we have the maximum demand and we have the load drawn by each of the stations. So the first question is they've given us a load factor. So as I said, once you write the parameters, you know, because you know that load factor is what? Number of units, over 8760 by the maximum demand. So using this equation, we can find the number of units because we have the maximum demand given to us. We have the load factor given to us. We can find it. So writing your parameters down helps a lot. The next is what you find the diversity factor. Diversity factor is a sum of all the loads divided by the maximum demand. So all the loads, so the load from this station, the load connected to this load here, this load drawn here, this load drawn, this load drawn, sum all of them together, divided by the maximum demand. That'll give you the diversity factor. So that's what was done here. So the sum of all of them divided by that will give us 1.903. Okay, yes, so we have it there. The next is to find the demand factor. The demand factor is the reciprocal or the inverse of the diversity factor. So that one is it becomes the maximum demand over the connected load. So the maximum demand 22,000 over some of the loads connected. Okay, so yeah, so it's not the formulas. So someone can write down all the formulas like on just a sheet of paper and then take a picture and send to the class group. So that's why we can just look at the formulas as we are preparing. Okay, let's move on, please. The next thing, is this. A power station is to supply four regions of load whose peak values are this, and this. Okay, so these are the peak values of the regions. Four, 1, 2, 3, 4. The diversity factor at the station, so they're giving us the diversity factor to be 1.5. And the annual load factor is 0.6. Okay. First question is to calculate the maximum demand. Now, writing the parameters, you know that the demand, the diversity factor, sorry, is given by the sum of the loads from each of the stations over the maximum demand. So we've been given the diversity factor, we've been given each of the loads, right? So we can sum them. So the maximum demand will just be the sum of all the loads divided by diversity factor, 1.5. So you sum 10,000 kilowatt plus 5,000 kilowatt plus 8,000 kilowatt plus 7,000 kilowatts all over 1.5. Okay, and that will give you the diversity factor. That will give you the maximum demand, sorry, the maximum demand. Then the second part is for us to find the annual energy supply from the station. This annual energy supply is the same as the unit, the same as the number of units generated, right? Energy, the number of units is in kilowatt, and it is in kilowatt hour. That's the unit for energy. So, sorry. So once again, we know that the load factor is given by the number of units generated. Sorry, it's given by the number of units generated all over 8760 by the maximum demand. So the maximum demand we found here. So we can see the maximum demand we found here will be there. So if I want to find the number of units generated, I'll just cross multiply. So that's the load factor times the maximum demand times 8760, and that's about it. So knowing the formulas is a very good start. Knowing the formulas by heart is a very, very good start to knowing what to do when you see the question. Okay, let's move on, please. Okay. Yeah, so this question, I'm coming, please. Hold on for some minutes. Okay, please, we are back. So the next question, yes, the next question is we are supposed to first determine the thermal efficiency of a power station and its coal bill per annum from the following data. Okay, so let's start. So we're supposed to first find the efficiency. To first find the efficiency, the thermal efficiency of a steam generator is given by the product of the efficiency of the turbine times the efficiency of the condenser. Okay, so we can see they gave us the boiler efficiency, and the turbine efficiency. So multiply them together. So that's what was done here. That's what was done here to get the efficiency of the power station. Now, second, we are supposed to find the bill, the coal bill per annum. Okay, so we are supposed to find how much. So the coal bill per annum is like how much we pay in a year. To find the coal bill per annum. Now, what do we need to know? What do we need to find? We know that we've been given the coal consumed to be it consumes 0.876 kilogram of a unit. Like per any unit produces a kilogram of coal used. Okay, so I have load factor to be 0.4. So my load factor is 0.4. So what can I find? If I know the price of 1 ton of coal. Okay, 1 ton is like, so 1 ton of coal costs this amount. So it means that if I'm supposed to find the total, if I can find the total number of tons, I can multiply by the price of 1 ton. So that's how we solve this question. So I have the load factor to be 0.4. I know that my load factor is equal to number of units generated, divided by 8760. 8760 is the number of hours in a year. Okay. Times 8760 by the maximum demand. So I can find the number of units generated here. I can do that. So let me do that. My number of units is given by load factor 8760 times maximum demand times the maximum demand 20,000 kilowatts. So that will give us the number of units generated to be this amount. Okay, 7008 times 10 to the 4. So I'm getting 7008 times 10 to the 4 kilowatt hour. So this is the number of units generated. Now, why do we need to find it? We were given the coal consumed, that it consumes 0.8 kilogram per every unit. So I can use proportion. To find the number of kilograms that will be used to generate these units. Okay. Yes, so I have it like this. So the number of units, I have the number of units. So now I can say that if 1 unit, if 1 unit, okay, is equal to 0.876 kilogram, 0.876 kilogram, then this number of units, is giving me how many? It doesn't make sense. This number of units is giving me how many kilograms, let's say X. So I can find this by multiplying this and this. So the mass in kilogram X we're given by 7008 times 10 to the 4 times 0.0 times 0.876 kilogram. So that's how this calculation was done. So you can see here, this kilowatt hour times this is giving me the coal consumed in kilogram. The coal consumed in kilogram. Okay. So if you multiply, I'm coming, let me do the multiplication. So we are getting 7008 by 10 to the 4 times 0.876. 0.876. So that's giving me 61390080 kilograms. So this is in kilograms. But if you check, we're given the price of 1 ton, which means I have to change the kilograms to ton to tons. Okay. So let's move on. So now I'll say that if 1000 kilograms is equal to 1 ton, 61390080 kilograms will give us how many tons? So I can find that one here. So that one will be a product of this and this divided by this. So your y will be 61390080 over 1000. So this will give us, let me see, 1 2 3. So this will give us this. So we'll get in tons. It means that we need 61,390.050 tons to generate this unit of electricity. Does it make sense? So now I can come and do my final thing, that if 1 ton costs this, so now final proportion, if 1 ton costs that amount, then this tons will cost how much? So it will just be a product. So you multiply this amount by, you multiply 61,390.050 by 29.53, and that will give you this Ghana cedis. Okay. So you will do, see here he joined everything together, but like I wanted to break it down so that we'll know how it came about for more understanding. So I'm having this times 29.53, and you are getting 181249.40. Okay. All right. So that's it. So you can see that everything starts with knowing the formulas, and then you know how to manipulate them. Okay, let's move on, please. Like, how do I cover the answer? How do I cover the answer? Something. What do you do is something here, but there's nothing. Share. Okay, let's move on. Come, let's do this. No. So this is the next question. So this is a question under tariffs. Okay. So this, as I said, we compiled all the questions. We compiled all the questions together. So a generating station, has a maximum demand of 50,000 kilowatts. Calculate the cost per kilowatt hour. So let's find the cost per kilowatt hour. So first, you must know what we are finding. We are finding the cost per kilowatt hour. Okay. Which means that what do I need? I need to know that my total costs. I need to know my total number of units. So that I'll divide them. That will give me my cost per kilowatt hour. So first, the question has been broken down now. So first thing, we can find our total cost. How do we find our total cost? You know that for every generating station, the total cost is given by the sum of the fixed costs plus the running costs. So the running costs are the tax, wages, and salaries. Like as you are running, so the amount you spend on fuel, the amount you spend on maintenance, and all those things are running costs here. So from this example, these are running costs. These are running costs. Okay. Yes. Also, you also know that your capital costs also play a role. Although you maybe your capital cost involves your the land, the fixed charges. The fixed charges involves your capital cost. And that one involves, like, even though maybe you bought your land, you bought your equipment, but then you pay wages on them, you pay tax on them, right? So those ones account for the capital cost as you are operating the system. So the fixed cost is, there's a one-time cost, but then there's also continuous cost due to payment of tax and everything. So we have the rate of interest here. So this rate of interest is specifying how much of the capital cost is actually accounting for the running cost or the cost of operation. Is that up is making sense? So the total annual cost, one, it depends on the running cost, as we can see. Yes, in a year you have paid your workers, you have bought fuel and oil, yes, but also a certain fraction of your capital cost that exists will also add to it. And this rate of interest or depreciation is specifying by what factor of the fixed cost is adding to the total annual cost. Yes, that's how best it can be said. So they told us that the rate of interest or depreciation is 10%, which means I have to find 10% of the capital cost. So I'll find 10%. So 10% is 0.1% of the capital cost, 95. 10% is 0.1 of 95 times 10 to the 5. So this is the cost arising from the capital cost. So that I'm finding my total cost. Okay. So it will be this plus the running costs, which we can see as our 9.5, 9 times 10 to the 5, and 6 times 10 to the 5. So 9.0 times 10 exponent 5 plus 6 times 10 exponent 5. So if you sum these two, this become 9.5 when you multiply. So if you sum the two, you get 24.5. 24.5 by 10 exponent 5. This is in Ghana city, this is cost. So right now we have our cost, yes. Once we have to find out total unit, so we can do our costs per unit. Okay. So let's see. What do we need? We have our maximum demand, we have our load factor, so we can find our total number of units. As I said, knowing the formulas is a good start. Because we know that our load factor is given by our number of units generated annually over total number of hours in a year, 8760, times the maximum demand. So our cross multiply, I can find the number of units generated. Number of units generated is the load factor, 0.4 times 8760 times the maximum demand. Maximum demand is 50,000 K. The load factor is 0.5, sorry, 0.5. This is 50,000 K. So when you multiply this, you get by this much, 21.9 times 10 to the 7. 21.9 times 10 to the 7. 21.9 times 10 to the 7 units. So that's in kilowatt hour. Note the unit very well. This is in kilowatt hour. This is in Ghana cedis. So I'm supposed to find the cost per kilowatt hour or the cost per unit. So that means I have to divide this amount, 24.5 times 10 exponent 5, over, this is in Ghana cedis, over 21.9 times 10 exponent 7. So this is it. This division will give you your cost per kilowatt hour. Let us multiply it. So we are doing, yes, 24.5 by 10 to the 5 divided by 10 to the 7. So if you do, you get 0.0111. This is in Ghana cedis. You can leave your answer as this. If you don't know how to change these two, first, leave your answer. But if you multiply this by 100, you get your answer in first. So by 100, so I'll get 1.1. I think yes, it was 180 here. So you get 1.12 pesos. You get 1.12 pesos. Okay. So that is it for this question too. So we're supposed to find a cost per kilowatt. They could have said find the cost per unit. Means find your total number of units, find your total cost, and divide the two. So that's how you analyze the questions. Okay. Now the next question is on economic load dispatch. This economic load dispatch is a concept that you have two generators, right? Yes, so you have two units supplying. Okay. You want to know how much each of them will supply and then the incremental fuel cost. So we have two units. Let's say unit one here, we have unit two here. They've given us the incremental fuel. So the incremental fuel cost is df1, like differential of the fuel with respect to the output. So df, so for the first one, it's df1 is given by this, df1 dp1 is this. Okay. Note that he could have given us another question where we know that f1 is, let's say, 2p1 plus 3, right? Let me say no, this is 2p1 squared plus 3p1 plus 4. So before, for a question like this, before you start solving, you will have to differentiate. So just know that there's no way that he'll give us this one. So it means if you are supposed to find your df1 dp1, differentiating from first principles, you get a 4p1 plus 3. So this is what we'll use in our solution if they don't give us the incremental fuel cost straightforward. Okay. So let's see. So we have our incremental fuel cost for the first unit. We have it for the second unit here. Now we know that from the principle, from the Lagrange multiplier connections, we know that df1 over dp1 must be equal to df2 over dp2 must be equal to df3, which is equal to a certain constant here, the incremental fuel cost lambda. Well, let me write it all. So this is equal to lambda. Okay, so we have all these parameters given to us. Now we're supposed to determine the economic distribution of load between the units for a plant output of 100 megawatts. So we know that these two plants, they combine to supply 100 megawatts, which means that we can form a first equation from that, that the power supplied by unit 1 plus unit 2 is equal to 1000 megawatts. I'm saying 100, sorry, 1000 megawatts, my equation 1. Also, using this Lagrange multiplier connection between the incrementals, we can also get another equation. So I know that my df1 dp1 is equal to df2 dp2. So I'll equate these two. I want to see these values. So 0.008 p1 plus 8.5 must be equal to the next one. And the next one is 0.0096 p2 plus 6.4, equation 2. So you have two equations, two unknowns. You solve, punch in your calculator. So you get this to be 200 megawatts. You get, sorry, I was thinking of another question. So we'll get P1 to be 454.55 megawatts. Get it to be 545.55 megawatts. So we have it like this. Okay, let's move on, please. So this is the first set of questions that can come. And that is economic dispatch. They'll give you two units. They'll give you their incrementals, and then you're supposed to find the power supplied, generated by each of them, each of the units. Now the next question is for us to find the corresponding incremental fuel cost. That is the delta. That's the lambda. That's the lambda. It's a lambda. But so we know that we know this, right? So now that I found P1 and P2, I can just put it inside. So it means that now I know this. So if I put P1 here to give me a lambda, and that should be, it should give me the same answer as if I put P2 here. I'll get the same answer. So if you check, if you do it, you get $11.636 per megawatt. Dollars per megawatt. Yes. So hope this is revision enough. I mean, you are remembering the things that you've learned. Right. Let's move on, please. Now, another way we can have it is this way. Sorry. So the next question: a power system consists of two plants connected by a transmission line. The only load is connected at plant 2. So let's try to picture this. So I'm having two plants. Okay. I'm having two plants. Plant 1 and plant 2. Plant 1 and plant 2. They said the load is connected at plant 2. The load is connected here. This is my load. So if plant 1 generates, when 20 megawatts is transmitted from plant, so if plant 1 generates, plant 1 will have to supply to plant 2. Then plant 2 will add its power to it and deliver to the load. So that's how the system is working. Right. So now this is a transmission line. When it's transmitting the 200 megawatts along the transmission line, there is a loss of 16 megawatts. Let's note. So now we are supposed to find the required generation for each plant. For each plant, that's what you're supposed to find. Okay. Now, when the losses come in, then the Lagrange equation becomes modified. Whenever there are losses, size. Okay, so the Lagrange equation therefore now becomes df1 dp1 times a certain constant L1 is equal to df2 dp2 times L2. What is this L1 and this L2? This L1 is equal to 1 over 1 minus dp loss over dp1. This L1. L2 is 1 over 1 minus dp loss dp2. So which means that I'm supposed to know what my dp loss dp1 and my dp loss dp2 are, so that I can find my L1, L2, and then I can know what I'm supposed to find. Okay. Yes, but let's know that in this question they've given us lambda. They give us a lambda to be the power received when the incremental fuel loss fuel cost lambda for the system is 12.5. So we have our lambda. So we know that all this is equal to 12.5. Let's keep this in our mind. Ooh, it will be useful. It's too big. So we have this to be 12.5. Okay. Yes. Let's move on, please. Let's move on. So now there's an equation that was stated emphatically that for any two plant power system, the P loss, and please you can remember this equation easily. P1 squared B11 plus P1 squared B11 plus 2P1 P2 B12 plus P2 squared B22. Now they are it's like matrices. So we have B11 here, we have B12, B21, B22. So that's how it is. So if you want to remember this equation easily, just remember the matrix, the position of the matrix element. So first one is squared, P1 squared times this squared plus 2 times B12. That's like that, adding this and this together. B12 and B21 are the same. So 2P1 P2 B12 plus P2 squared B22. So you can remember this. This is equal to the P loss. Now let's pay attention here. Let's go back to what I drew. Now, if you observe this thing, this setup here, we can see that yes, there's a power transmission line connecting 1 to 2, where the power generated at 1 is transmitted to 2, right? Which means that we can see that we don't transmit the power from 2 along this line. So the loss on this line is dependent on the power from the 1 only. Does it make? Which means that any factor that has a 2 inside, which means that this B12 and this B22 are not contributing to the loss on the transmission line, only the loss coming from the first plant. So this element, this component goes to 0, this component goes to 0. So I can say that my P loss is equal to P1 squared B11. Please, I hope I'm making sense. So I said that we didn't transmit power on this transmission line. So the loss in the transmission line is due to power coming from only generator 1 here, or plant 1. So every component with 2 inside vanishes. So here I can find my B11 as the loss. They gave me the loss to be 16. Then my P1, the power transmitted was 200. So I'll find 200 this, and this will give me my B11 to be 0.004 per megawatt. Like this. So you have it like this. Okay, so this is your B11. Now, why are we finding this? Don't forget that in all we are trying to find is this 1 over 1 minus dP loss over dP1, right? So if I know this to be my P loss, let me find dP loss dP1. So that will give you what? 2P1 B11, right? 2P1 B11. Also, let me find my dP loss dP2. There's no P2 component here, so that will give me 0. So I can come and put these values here. Okay, so let me clean this side. Alright, so a bit it makes sense. Yeah. So I can find my L1 to be equal to 1 over 1 minus 2 times, so I'll get 0.0008 P1. And I'll get my L2 to be 1. Okay, so now I know this. How do I move on to find how much each of them will generate? Now I know that the F1, the P1, L1 is equal to 12.5. So I'll apply that. So the F1, the P1, the P1 was given the question. The F1, the P1 was 0.01 P1 plus 8.5. This, so I'm using this times L1, that is 1 over 1 minus 0.0008 P1. This times this is supposed to be equal to 12.5 incremental loss here. So now you have an equation, one unknown, you can find, cross multiply, group like terms, you get your P1 to be equal to 200 megawatts. Also, we can use this equals this to find P2. So now, because now I know what L2 is. I know what L2 is. L2 is 1. So I'll do 0.015 P2 plus 9.5 times 1 for L2. Supposed to be equal to the incremental 12.5. So if you simplify this, you get P2 to also be equal to 200 megawatt. So that's about it. So we are done with the first part. We are supposed to find the required generation for each plant. So each plant is supposed to generate 200 megawatts of power. Each plant is supposed to generate 200 megawatts of power. Now the next is to find the power received by the load. So we know that this will generate 200, right? 16 will get lost. This will generate 200 too. But this one, it must be transmitted. It just supplies to the load. So then the power the load will get will be 200 plus 200 minus 16. That will give us 384 megawatts. So this is the power that the load will get. This is the power received by the load. Does it make sense? It should. So if you have a question for two plants given, and I have a feeling this question will come. So like after like let's go through this question. I have a feeling this question will come. It's part of the question that my gut is strong about. I have a strong feeling about it. So this what do we have to know? We have to know that our P loss is given by, for any two power system, is given by P1 squared B11 plus 2 P1 P2 B12 plus P2 squared B22. Then we said that because there's no transmission from 2, any component with 2 goes away. So my P loss becomes just this. And if this is my P loss, I know that my LK is 1, or let me say my L1 is 1 over 1 minus dP loss dP1, right? I have to find dP loss dP1, simplify. Same for L2. Then I'll use this equation to find my B11. So if I know what my B11 is, then I can move ahead and solve the question by knowing that dF1 dP1 L1 times L1 is equal to lambda, and also dF2 dP2 times L2 is also equal to lambda. Okay, so that's how it will be simplified. That's how it has to be simplified. Sorry, that's how it has to be simplified. This self-assessment test question looks like the one we solved. So we've been given maximum demand to be this. We're given maximum demand to be this. We're supposed to find the cost per kilowatt. We have to find the total cost. Find the total number of units and divide. So we have our load factor here, maximum demand. We can find our number of units as 8760 times load factor times.
Different. Doesn't be different. I don't get it.
So these are number of units. 8760 times 0.5 times the maximum demand, 60,000. So that gives us number of units in kilowatt hour. Okay. So now that we have this, we have to find the total cost. Now let's look at something here. See, in the other one we had our capital cost, and we also had our interest and depreciation rate, so that we could just find the factor. But here they've given us the interest and depreciation rate straightforward. We have our running cost here, so we will neglect the capital cost when we are solving. We will not use the capital cost because we already know how much of the capital cost is adding to the annual cost. I hope it makes sense. Yes. So we sum these three together, give us our total cost, and divide by the number of units we'll get here. Okay. So that's it. Okay. Now per unit. Let's move on to per unit. Now per unit. In answering per unit questions, what do we know? First scenario, we'll be given actual impedance. You're supposed to find the per unit impedances. So in that case, your ZPU is equal to your actual impedance times your power in MVA over, it's called MVA base, over your voltage in kilovolts. So this is it. You have to remember this. Okay. Me, the way I've memorized it as ZPU is equal to Z actual times power over voltage squared. Sorry. Yes, over voltage squared. Knowing that my power is in MVA and my voltage is in kilovolts. So that is power over voltage squared. Power over voltage squared. Power over voltage squared. Power must be in MVA. Voltage must be in kilovolts. So that's how you that this is one scenario. The second scenario is where someone says right. Right. Yes, so I was saying that here I memorized it as ZPU is equal to Z actual times power over voltage squared. Knowing that my power is in MVA and my voltage is in kilovolts. This is the first scenario. Second scenario of a question is where they will give you a first ZPU was found. Okay, so there's a ZPU found under some base values. So there's a first ZPU found under some base values. And then now they are giving you different base values to find a new ZPU. So in that case, the equation becomes this way. Our new ZPU is equal to our old ZPU times first is times the power. Okay, but the power is still new over old. So plus KVA new over KVA old. Just pay attention to this new and old. Times for the voltage it is old. V old over V new. The voltage is always squared. Keep it in your mind. Okay. So we need this equation here. We also need this equation here. These are the two equations we need to solve the per unit questions. So let's move on. Let's see where the law takes us. All right. So here we're supposed to convert this to per unit using these as our base value. So this is the first scenario. So here we know that what as ZPU is given by our actual times power in MVA. Power in MVA. So change it to MVA. Change it to MVA. You form another K. So this will become 1 MVA. So 1 MVA over voltage in kilovolts squared. So that is over 11 squared. So you are getting 2 over 11 squared. So that is important to know the equations. This will give you 0.0165 ohms. No, per unit. 0.0165 per unit. Okay, so that's what we have here. Okay, yes. Now, another question here. We've been given an 11 kilovolt 15 megavolt amps generator has a reactance this per unit referred to its rating. So this per unit values was found at these base values. Now they've chosen the new base values to be this 110 kilovolt and 30 megavolts, and they're supposed to find the new per unit. So this is the second scenario I was talking about. So here your ZPU new is given by your Z old 0.015 Z old times first is power. By which power? The power 2 is new over old. So the power is new over old over times voltage. But the voltage is old over new. Voltage is old. 11 over new 110. Because they are in same units, I'm not bringing in units, then squared. Don't forget it has to be squared. Voltage has to be squared. So this is it. So ZPU new is ZPU old times power. The power is also new over old. Then your voltage is old over new squared. So you simplify this and then you get 0.03 per unit. 0.03 per unit. Okay. So after, I'll make Papa write all the formulas that like we are seeing on just one sheet of paper, so that you'll be looking at it before you enter the exam hall. So I'll be very familiar with them before you enter the exam hall. Okay. Yes, please. Okay. So I have a question here. Hurry up, let's move on. Okay. Okay. So now we have another question here, another interesting question here. We have a single phase transformer. Okay, so we have a transformer with ratings 400 per 200, and the power 10 kilovolt amps, the same power for here, 10 kilovolt amps, and it has a reactance 2 ohms referred to its high voltage. So the reactance here, the reactance is 2 ohms referred to. So this is the high voltage. The high voltage side here is a primary winding. Okay, so the reactance referred here is 2 ohms. Is that really which question?
Let's look up something.
All right, sure. So the first question is for you to calculate the per unit reactance on both sides. So first, let's come to the high voltage winding side. Let's find the per unit reactance here. So here, this is a scenario where you just use you have the base values, and we are supposed to find the per unit. So our ZPU is Z actual 2 times the power in megavolt amps. The power in megavolt amps. So here we have 10 kilovolt amps. 13 to megavolt amps, I'll divide by 1000. So that will be 1, 2, 3. So yes, I have 10 here. So that will be 0.01. So I get 0.01 over the voltage in 0.01 over the voltage in kilovolt squared. So the voltage here is 400. In kilovolts, I'll divide by 1000. So that will be 0.4 squared. So this will give you 0.125 ohms in per unit. This will give you 0.125 ohms in per unit. Okay. So this is it. Now the next part says that find the per unit referred to at the other side. So at the other side, first what I must do is that I must first refer this impedance to the low winding side. I must first refer this impedance to the secondary side, the low voltage side. Okay. So if you are referring from primary to secondary, it is A squared times Z. Keep it in your mind. Z secondary is A squared times Z primary. What's our A squared? Our A squared is this ratio here. This ratio. Secondary over primary. So 200 over 400 squared. Okay. So I'm saying that secondary impedance is given by A squared times primary impedance. What's our A? Our A is V secondary over V primary squared times Z primary. So this will give us V secondary 200 over primary 400 squared times 2. So that will give us 0.5 ohms. If you solve it, you get 0.5. So which means that I'm having 200 volts here and an impedance here of 0.5 ohms. Okay, and then the power remains the same, 10 kilovolt amps. So I can find my Z per unit here to be Z actual times power in megavolt amps 0.01 over voltage in kilovolt squared 0.2 squared, and you get 0.125 ohms per unit. So this confirms that in transformers, if you are working with per unit, the impedance at the primary side and the secondary side are the same, we will not have to worry about the anything. Once it's in per unit, I can use the impedance at the primary and secondary side to be the same. I will not have to convert or refer it to any side. I hope that makes sense. Yes, it should. So that's it. That's it for that question too. That's it for that question too. Yes. So that's so ZPU at the low voltage winding is equal to ZPU at the high voltage winding. And then you have that. Yes, and this question too that will come.
Yeah, the question is also then the policy.
How many?
This is the points.
Wait for it. Okay, sure. So let's keep this question and let's solve this last question here. Let's solve this last question here. Okay. So so we know that for any wire, for any piece of wire, for any piece of wire of a certain length and a certain cross-sectional area, the resistance of that wire is given by rho L over A. The resistance of that wire is given by rho L over A. Okay. Now, resistance is resistance depends on temperature. Resistance depends on temperature. Okay, so for changing temperature, the resistance will not be constant. So although this is a resistance, but this is a resistance at, let's say, room temperature. So this resistance value is taken to be the resistance at 20 degrees Celsius. So anytime you do this rho L over A, you are finding resistance at 20 degrees Celsius. If you are supposed to find the resistance at any other temperature, then you use the second equation. So the resistance at a temperature theta is given by resistance at 20 degrees Celsius multiplying 1 plus alpha. This alpha is the temperature coefficient of resistance, multiplying the theta. Theta is that temperature we are measuring the resistance at now, minus 20 degrees, and you have it like this. So for those questions, so these are the two equations that we need for that particular question. Okay. So let's see how it works. So we've been given the resistance, we've been given the diameter. So we know that a piece of wire is cylindrical, right? Yes, it's cylindrical. This is how every wire looks like. So we have to find the resistance at 20 degrees Celsius and at 50 degrees Celsius. Okay, so now we know that our resistance at 20 degrees Celsius is given by rho L over A. So I think we are supposed to, in this question, they didn't give us the resistivity of copper or of aluminium. I don't know why they didn't give it to us. I think it should have been given to us. But it's here. 3.22 times 10 to the negative 8. So let's try to memorize it and maybe do not give it to us again. But he's supposed to give it to us. So we have this resistivity times the length. The length is 304.8 meters times the diameter.
Not on that one, actually.
Let's keep it. No, it's not. No, it's not. Skip it. Sorry, please, I'm coming, okay? I'm clarifying something. I think so. Let's keep it. Let's move on, please. So yes. So now we have to find the cross-sectional area, and as I was saying, that is what is cylindrical. So we can find the area of a circle, right? The cross-sectional area is a circle, of a cylinder is a circle. So our area becomes 1 over 4 pi d squared. So you find this area and divide it by, bring it here. So 1 over 4 pi times d squared. 7 point. Be careful about this milli squared. So milli is 10 to the negative 3. Then you square everything. So this give you your resistance. This give you your resistance value. So when you do that, you get 0.204. And as I said, at this is the resistance at 20 degrees Celsius. The resistance at any other temperature is given by this. So we'll put in 20 degrees Celsius here. We have our temperature coefficient of resistance here, and we have our R at 20 here. So we can find, and you will get this. Yes, so that is about it. Let's move on to the question I skipped. After this, we'll talk about the sizing of generators. Okay, we'll just talk about the ones that we've not answered the questions on yet. Those are the ones I'll come. And then we will all go and is the power generation and supply exams. All right. So we have a question. A 100 megavolt 33 kilovolt three-phase generator has a sub-transient reactance. So let me try to make the sketch with the values on it. All right, let's move on, please. So I'm having a generator here. This generator has power 100 megavolt amps, voltage 33 kilovolts, and a reactance, a per unit reactance of 0.15 is a generator. Okay, it is connected to the motors through a transmission line and transformers as shown in the figure. So you can see the figure there. So we have motors. We have first we have our M1. M1 has 30 megavolt amps. They are all at 30 kilovolts, and they all have XPUs of 0.2. So this M1 is the rating of M1. M2 has a rating 20 megavolt amps. M3 has a rating 50 megavolt amps. So these are the three generators we are talking about here. And it says it's passed through two transformers, delta star. Then we have another star delta transformer, first connected to the motors. Okay. So we were given for the transformers, we were given the three-phase transformers are rated as 110 megavolt amps, 33, 32 kilovolts, 110 kilovolts with leakage reactance. So here the XPU here is 0.08 per unit. Using the generator rating as the base quantity. Now, so pay attention, okay? So this is what I was talking about. You see, these components or these devices, they have their per unit ratings here. Yes, per unit 0.2 per unit, yes. But these per unit values were gotten at their corresponding base values. And now they say find a new reactance using these new base values. So it's straight ahead, you should start thinking that we'll be using ZPU new is equal to ZPU old times KVA new over KVA old times KVA old. Yeah, here MV and KVA, but they should be in the same unit. KVA old over KVA new all squared. So you start thinking that we'll be using this equation. Right, all right. So the first part of the question says that Using the generator rating as a base quantity in the generator circuit, determine the base quantities in other parts of the system. Determine the base quantities in other parts of the system. So we can find the base quantity here on this transmission line, the point of connection between them. And then we can also find the base quantities for the motor here using this side. Okay. So how do we find the base quantities? How do we find the base quantities? Let's see. The base voltage. Let's find the base voltage. So I have here, you use proportion. You use proportion. You just say that, okay, this 33 kilovolts is supplying, right? Is what's coming here. It comes to me 32, right? How much will 33 give you? So you say that if 32 is giving you 33, how much will 110 give you? This is the supply. It's coming here. So over here we have 33 on this line, this connection here, 33 kilovolts, right? Coming to meet a 32 kilovolts by 110 kilovolts transformer. So if 32 corresponds to 33 here, then this 110, what does it correspond to? Okay, so it's like, let's say how much of the 33 will come to this side. Take it like that. How much of 33 will come to this side, will come to the transmission line? I can say my x is given by 110 times 33 over 32. 110 times 33 over 32. That will give you 113.4. 113.4 kilovolts. Okay. So think of it as, again, this is the rating of the transformer. Yes, 33 comes. How much will 33 give? So if 32 is giving us 110, how much does 33 give at the output? We'll give this amount. So this is the base value for this transmission line here. This is the base value coming here. So the base value coming here is 113.4. Now, how do we know the base value at this side too, on this line? Same. The rating of this transformer is 32,110, right? But if we check this, this is a step down transformer, because now here we have the 110 connected to. So if this transformer has rating 110 kilovolts, 32 kilovolts. So for this transformer too, we'll say that we want to find how much this will give here. So we'll say that if 110 is equal to 32, how much will 113.4 give us? It makes sense. So our y will be equal to 113.4 times 32 over 110, and that will give you 33 kilovolts. So here the base I'll be using here will be 33 kilovolts. That's the base I'll use here. I hope it makes sense. Yes. So it makes sense. Right. If that doesn't make sense, ask any question you want to ask. Check any question. That makes sense. So these are the new base values in the other part of the circuit, this and this. Now we can move on and answer the question. Now I'm supposed to find the corresponding per unit values at the new base. Corresponding per unit values at the new base. Okay, let's move on. The corresponding per unit values at the new base. So let's see. So for the generator, we only have a new value, no, because its initial ZPU is 0.15, and since we are using its parameters as the new base, it will not change. So the generator will have the same. Sure. Now the next, let's look at the transformer. Let's look at the transformer. So our ZPU new is equal to our ZPU old. So the equation, please, I'm not writing the equation, but try to picture it. Our ZPU old. So for the transformer, our ZPU old is 0.08 times times MVA new. MVA new, we are using a new base is 100 over MVA old. Are you following? Yes. Times RV old. RV old is 32 over RV new 33 squared. This is how it makes sense. So we are using this side. So we are finding here. Refer to this side. Okay. Yeah. So that's what you get. So if you do it, if you punch in the values, you get your ZPU new to be equal to 0.06 0.06838 per unit. We will have, so this is what you get. Now let's find for the transmission line. So for the transmission line, our ZPU is given by what? Our ZPU is given by, let's watch, our Z actual. So this one, we don't have any old, we have the actual to be 50. So our Z actual times power. So the power on the line, the base power is what? The base power is 100, right? Oh, are they seeing it? They are seeing it. So sorry, I'm quickly close it. So for the transmission line, our ZP is our Z actual, that's 50, times our base power, 100 megavolt amps, over our base voltage in kilovolts. So remember that we found it for the transmission line, we found the voltage along this line to be 113.4. So that's what I'll use. So that's what I'll use there. So I'll do 113.4 squared. So if you do it correctly, you will get it to be 0.3886 per unit. That is what you have. Okay. The next is for us to find for the motors, for each of the motors. So if you take motor 1, our ZPU new is our ZPU old times MVA new, right? MVA new, that's 100 over the first motor's MVA is 30 times V old. The V old here is 30 over V new 33 squared. So you do this. Then you find for motor 2, ZPU new is 0.2 times new over old MVA is 20 times 30 over 33 squared. And for the last one, the last motor, same, but here I'm having 100 over MVA old 50 times 30 over 33 squared. So there you have it. So yes, that's it. Here, here. We found this. We use our proportions to find our new values here. So that is it. Check it on my question, Papa. Please, if you have any question, kindly ask, okay? If you have any question, kindly ask. So I hope it makes sense. Yes. I thank God it makes sense. No one is asking any questions, so it makes sense. So we have seen the questions. So we've seen the questions. So we've answered this. I'm just scrolling through. We've seen this question. All right, please. Just some few minutes. Coming. Okay. No.
So please, you can check the. So please check the description box for the link to the PVs. We are now about to do them, right? So we'll walk through the entire PV sizing technique, all the 9 steps, how to size them, and then we hope that at the end you would be satisfied. Yes, then we'd end the stream on a good note. So please, a few minutes for you to quickly get. So just check the description box. You see a second link there. If you're not seeing it, okay. So if you're not seeing it, please check the class group or check the second link. Refresh your page or something, and it would appear. So you 2 minutes to. Yes. And yes, if you've not subscribed, you will see that the live chat is disabled for you, right? So maybe that may be a reason why you're not asking your questions. So please do subscribe, and then instantly you'll be able to send in questions so that we do them for you. Have any recommendations to maybe you don't understand something, we'll get to it. And Arinzi, please, we saw your question on the L1 and L2. If you could please just go back a little. I'm sure you would be fine. Just scroll back a little and then check if you understand. If not, then we would look at it. But basically, those two are just the formulas. The formulas is not just for this question. They are general formulas, so you can use them. Right? You can feel free and then use them. You understand? So please let's hurry up with this. Thank you.
So we are looking at the size and all the steps are here. Yeah. How? All right. So let's start, please. Now, let's see. Let me make an annotated sketch here. Yes. So I'm drawing the sketch that we use to like a representation of the components. Okay, so welcome back. Welcome. Welcome. So how to read. Have a array here. Have charge control. Have a charge. Have a want to supply. Have to have an now can now then we can now supply to AC loads. Then I have a battery here. So now, what is the first thing you do? What's the first thing you do? Let's go through the steps before we start learning. Like I want the steps. Has to be familiar with the steps. First thing you do is to find your system. So you find your system voltage. That's the first thing you do. Find your system system voltage. The second thing for us to size our inverters and converters. So this is step 2. Step 3 is sizing of inverters and converters. That's step 2. Step 3 is for us to find our daily energy demand. So let me put the E here. So step 3 is to find our daily energy demand. And we'll use this daily energy demand to find our battery bank capacity. So this is our step 4. You see how I'm doing it? So this will just make you know how we go about the finding of the topic. Now, after battery bank capacity, we have to size our PV array. But before we size our PV array, we have to find the maximum irradiation H. This is the 5. This is the 5. So after that, step 6, size our PV array. Step 7, size our charge control. Step 8, we'll size our protection. We'll look for the fuses. So step 8. And step 9 is the cable sizing. Let me do. So this is the steps. So it goes like this. If you remember the diagram, it just goes like this. Actually, like find your system voltage, size inverters and converters, find your daily energy demand, find your battery bank capacity, find your H. Okay, so find the sizing of inverters. The third one, you find your daily energy demand. You have put here E. Use that one together with other parameters. Find our battery capacity. Find our battery capacity. Now after that, we'll find our irradiation. Step 6, size the PV array. Step 6. Step 7 is sizing of charge control. Step 8, protection. Step 9 is cable size. Let's move on. This is what we have. So let's see. So the first step is for us to find our system voltage. How do we find our system voltage? How do we find our system voltage? Because if you want to find your system voltage, first thing is to list all the electrical components. You list all the electrical components that are in the room. So you have it like this. Let me just say this is it. This is a list of all electrical components. Find their corresponding powers. You find the total power. The idea is to find the whole idea is to find the total power. That's what we are doing. We find the total power. So here the compact lamps were two, right? Each operating 9. But then we know that for compact lamps, multiply by 1.1. For compact lamps, multiply by 1.1. And for fluorescent lamps, multiply by 1.2. So here I'll do 9 times 1.1. That'll give me 19. Then for fluorescent lamps, I'll do this times 1.25. That'll give me this. Now for AC components, you multiply their power by the efficiency of the inverters. The efficiency of the inverter, 85.85 here. You multiply their power by the efficiency of the get the power. Find your total. Now when you get your total power, what does it tell us? You use this table. When you find your total power, now come to the table and read where your system voltage is. If your power is from 0 to 500 watts, use the system voltage of it's between 500 watts and 2000 watts. In this range, you use this. So here, in this particular question, the power was gotten to be 1.49. That's between 0 and 500 watts. We are using a system voltage of 12 volts. That is a system voltage of 12 volts. So I can come here and that I'm using a right. The total power is 149, which is less than 500 watts. Therefore, system voltage is 12 volts. Now, in the every step that came, we didn't have, and even this step will not come. This step will not come. Okay, the second step is for us to size our converters and inverters. For us to size our converters and inverters. So what's the rating of converters should be? How do we know the rating of the converters that we produce? Let's see how we know that. So for converters, we use their nominal for converters, we use its nominal current. So we will choose a converter with a nominal current greater than the load current. To a nominal current greater than the load current times 1.1. They say we will use a converter with a nominal current greater than I downstream calculated current times 1. You have it here. Then for inverters, so this let me just do I times 1. Then for inverters, we are sizing inverters. We use a nominal, we choose an inverter that has a nominal rate greater than the rating, the apparent power times 1.1. And the inverter should also have a surge power greater than K times that same power. If our K, it may be 3. If they are motor system, if they are no motor system. So in the example above, how we find our S2? We find our S2 by we have two AC parameters here, right? Yes. So we know that our apparent power is given by active power over the power factor. So I'll do my active power over power factor. 50 over 0. So the S for this will be 50 over 0.8 plus the S of this 25 over 0.8. That will give me my S2. So my S2 is 50 over 0.8 plus 25 over 0.8. That will give me the total apparent power. Total apparent power. The total apparent power will be gotten to get it to be where is this? 93.75. This will be equal to 93. Then we say that with an inverter that has a nominal rating, so Sn should be greater than 93.5 and the SH greater than what we have multiplied times 93.75. So you yes values. That's it. So you get the value to be 102.187.5. So this step two. So step two is the size. Now the step three is find the daily energy demand. Step three is for us to find the daily energy demand. How do you find the daily energy demand? How do you find the daily energy demand? We know that E equals to power times time. So we'll go back to our table where we found the hours, right? And then we'll know the working hours. Hello. We know the working hours of each of the components. We can find their energy. Since we know the daily demand of each of them, we know the working hours of each of them, then we can find the energy. Now, okay, please, I hope you can hear me. So, through power times time, we also have to evaluate the current through each of the loads. But we'll use it in the future. But we just have to evaluate it in this step so that we don't have to draw the table again. So we have our total power here. So this time, this give us this time, give us this. Then we also find our current. Our current is power times system voltage, power over system voltage. So I'll divide this power by 12 volts by 12 volts. If you do 58.82 divided by 12, take note it is over system voltage. Over system, not over this 220 system voltage. So here we'll find the current that's given by power over vein system. We also find our total current here, total load current. And we also find our total energy here, total E here. Okay. Yeah, so if you check, we'll get our E total to be 544.95. Total load current to be 11.94. So now we found our energy. But then from practice, we multiply this energy by a security factor. Usually you choose, maybe you give it to us, but you choose. So here they use 15%. So that's multiply this value by 1.15 to give it a daily energy demand. Now we find daily energy demand. Come and size our battery. So we come and find. So we ask the 4 size our battery. We have to find the battery bank capacity. That is given by the total energy we found over the number of days of autonomy of the battery times battery efficiency times depth of discharge of the battery times the battery. These parameters will be given on the data sheets of you choose your days of autonomy and then you have this. You can find the battery bank capacity. So the battery bank capacity given by you find it, you get yes. So there's an example here. In this example, when you find your battery bank capacity, get this. Get 249%. This is the battery bank capacity. This is the battery we are supposed to provide. And now, how can we connect the batteries to achieve this capacity? How do we do that? So first thing, you can find the number of batteries that will connect in the number of batteries in number of batteries in string NBS. Number of batteries in a string. Number of batteries in a string given by the system voltage over the battery voltage. Given by system voltage over the battery voltage. In this case, it's 4 over 2. I'll give you 1. It means that I'm having just one module, just one battery like this. Have it like this. Now I want to know how many of such strings I have to connect parallel. Get this. So I'm doing number of strings in parallel. Number of strings in parallel given by the battery bank capacity over the charge of just one battery times number of batteries in it. That's given by, we found them. We're given the capacity of 1 to be 65. So I'll do my, sorry. So I'll do 249.77 over 65 times 1. That'll give us 4 batteries. Parallel. 4 strings in parallel, sorry. So therefore, the total number of batteries given by the product of this, that will give me 4. So the battery capacity that I'm supplying is 4 times 65. That's 260. And again, this can so yes, so step 1 has come. Step 2. So normally step 2 can come. Step 2, which is the size of the converter or inverter, it can come. Step 3 too can come. That is how to calculate your daily energy demand. Step 4, he says it will not come. Yes. Step 5. Step 5, you're supposed to step 5 is where we find our daily radiation. Now and you just read from it. Step 5 can come. Step 5 can come. And I will give it to you the H. Daily radiation. Step 5 can come. Step 6. So we finish it very soon. So in step 6 of it, now we have our H. Now we can size our PV array. We can size our PV. So here to we find our H so that we can find our PV array. Our PV. We can find our power that is given by the daily energy demand over battery efficiency times the rating factor times, we found the H already. They'll give us the rating factor. It's supposed to be on the name sheet of the array. This is a battery efficiency and the daily energy demand we evaluated. Yes, so we can find it. So from this example here, our daily energy demand to be 599.45. So therefore, 599.45 over 3.28. The 3.28 is representing the battery efficiency. That was given in the data sheet of the battery. Then we have our derating factor here. We have our battery efficiency here. And then, the 3.28 is the H, sorry, the radiation. This is our battery efficiency, and this is the rating. Get this. And we must know how to connect the batteries together. So we will find the number of modules in the string. That is system voltage power. I'll give us 1. Then we also find number of strings that are in parallel. So strings that are in parallel will be the PV array power. This array power, let me write it. The number of strings in parallel array over the P array of the P of model, right? Times number of like this. So yes, so the PV array power that we found is 285 over the power of the model will be given power of model maximum power 50 times 1. So I'll give it 6. The total number of modules is 6 and the peak power installed is 6 times each of them. That's 300 watts. That's how we size the array. This one too can come. This one has not come yet. Size of PV arrays haven't come yet. This can also come. This can also come. Step 7. Step 7 is the charge controller sizing. That one has come. Just one quiz I didn't take. So the charge controller, we have to know the nominal current of the charge controller, nominal voltage of the charge controller. The nominal voltage of the charge controller is given by the system. In this case, it's 12 volts. The nominal current, if you want to find the nominal current, you do this. You will find the maximum between two parameters. Parameters called IP Beijing and the I load. This I load is what we calculated when we were calculating the daily energy demand. We found the current. That's the I load. In here we had 11.94. 11.9. So between this and our IP version, which we'll find, which of them is big? Then your nominal current will be equal to that maximum, the largest among them. Let's find our IP region. Our IP region is our photovoltaic current, right? So now we know that we had six strings in parallel. That's six strings in parallel. Six. So how do I find the total current coming out for this? To be six times the current in each branch. That's the short circuit current. And that short circuit current is given on the data sheet. So it's here. So six times the short circuit current. Six times the short circuit current. Have it like that. Here it is. So yes, so six times the short circuit current, that'll give you 19.8. If you check 19.8 is 11.94, the largest is 19. We use that. If you use the six times the short circuit current, you get 19. So the largest between 19.86 and 11.94 is 19. So therefore, the nominal current is equal to 19. And your nominal voltage, which I said must be equal to the system voltage, equal to 12. That's how you size it. That's how you size the charge control. And the next thing is providing circuits. Next thing is providing uses for protection. Next thing is providing protection. Now, we must provide three kinds of protections. See, we have certain number of arrays, no, strings in parallel. So first, we must provide protection for each of the strings. So that protection, you use a fuse of rating. Its rating should be 1.5 of the between 1.5 of the ISC and 2 of the ISC. So this use a fuse of this rating. Provide, so this is string protection. Protection for string. Now, so that is so same protection. Now all these their current is coming to move to this side. So you must provide protection for the entire array. So protection for array is this, so you multiply by 6, but each is the 6 that's coming out. So it will be the number of strings in parallel times 1.5 times the short circuit current. I hope it's making sense. Yes. So because I provided protection here, yes, but each of these currents will come and flow through a single line here, right? The current here given by the number of strings in parallel is 6. 6, the number of strings in parallel, times the short circuit current times 1.5. This 1.5 is a multiplying factor is fixed. So here's 2. 1.5 and 2 times. Now last thing, provide protection for the battery and protection for the battery. That one you use a few whose rating should be greater than 10 equals to. That's how you go about it. That's how you go about it. Let's move on. Let's move on, please. Yes, so that's how you provide protection. You provide protection first. You provide protection for the array, for the strings, then provide protection for the array, and provide protection for the battery bank. Now the next thing is for us to, so an example is here. So you do that. You know that we have to use a fuse 4 and 6. That's 6. So they will give us a table of fuses. So from the answers you are getting, you calculate complete. The last is the cable sizing. Last, we any version, many of this. Last is the cable sizing. The cable size. The cable sizing now also involves a maximum between values, cross-sectional area. Okay, how do I know? How do I find A1? How do I find? How do I find A1? A1. A1. Now, see when you when you are doing the fusing, when you are doing the fusing, I say you provide three fuses, right? So you choose the largest fuse. So in this example here, largest fuse here, the fuse you can use is 32 ohms. Okay. So yes. So here 32 or 35 can fit, but I'll choose 32. Choose 32, yes, honest. Then now, so 32 is the largest fuse we use. 32 is the largest fuse that, right? Yes. So now we know, we'll go to the table of areas and cable sizes of current. So our 32 ohms fuse, we'll come and check. What is the current which is just larger than our 32 ohms fuse? The current just larger than our 32 ohms 36 here. So you see, so it's the fuses you use, pick the largest fuse. Come and check a current that's just larger than it. The current that's just larger than it is 36. Okay. And that 36 has a cross-sectional area of 6. So our first cross-sectional area will be using 6 millimeters. So it's 6 millimeters squared. How do you find the first cross-sectional area? I said that pick your fuse, the largest fuse that you use for your protection. Come to the area table and choose a current that's just larger than that fuse, and use a cable size corresponding to that. So here use 6. Now how do you find your A2? For your A2, you solve for it. Solve for your A2. So it's given by this equation. 2 rho, this is the equation you use. You know the parameters. This rho is the resistivity, the using copper of copper. This L is the length. So an example, we have our length with, we have our I. The I is a PV current. The I is the PV current, which is short circuit current times number of strings per. That's it. Your V max is your PV array V max on the PV array data sheet. And then the voltage drop is given by 3%. So you put in the values. This is the resistivity of copper. Yeah, so this one is an equation you're supposed to remember. 2 rho Li over change in V. So this is given by 2 rho Li over change in V. This V is a V max on the data sheet of the PV array. This is given by 0.0. This is the current flowing from the array. Current flowing here. Having six interval like this. Having six like this. With the current coming out of this. That's the short circuit current. Short circuit current times the number. Not the current. That's the current out. This is the length, this is the row. I can find my A. If you solve for the A in this case, you get the A to be 18 point. So you go to the table, check 18.32. There's no 18.32 on the table, but then the cable size that's just larger than that is 25. So I'll use a 25 millimeter square cable. So my A to 25. And you check between 25 and 6, of course. The largest is 25. So your cable size is 25 millimeters squared. Yes, so that is how you size tandem array. That's how you size the stand. So we've gone the chapter 4 and 5, gone through the saw the economic factors, saw the tariff, saw the dispatch, economic dispatch for 2. We also saw the how do you call it? The per unit calculations and then the resistance stuff. Then we came to the PV and let me just mention some last two things. Yes, the RLGC parameters. Those are the question and answer, but let me just mention the equation. Alright, so let me just mention one last thing. We know that the RLGC parameters, what are the RS resistance, RS series resistance, series reactance, shunt capacitance, shunt. So the resistance will be found. Let's just see the equation. So the resistance will be finding where we find the RS go L over A at 20 degrees. Then at any other temperature is R at 20 times 1 plus alpha. That temperature is R at any. Now now let's see the L. L the L is given by the capacitance. So let's just go at the L. The L is given by 4 times 10 to the negative 10 D over R, where the distance between conductors, have distance between conductors, and R is the radius of the conductor. Have radius. This is the distance between. This is the equation. This is the inductance of a single phase 2-wire line. Now the capacitance of the two lines given by I epsilon over n over R. Epsilon is the permittivity of the dielectric material. Place between two conductors. Now between conductors and ground. Now it is 2 pi epsilon over ln. For your conductance, just be the inverse of the resistance. That's so let's take note of it. So that is the end of the question solving for power generation supply. All the best. To revise, do the reading, hold the reading at 3. Let's go and ace. God bless you.